You are listening to AI Paper Podcasts, and today we are diving right into Helios' real-time long video generation model by researchers from Peking University, ByteDance, Canva, and Chengdu Anu Intelligence.
Right, and we need to hit the metrics on this one immediately because they are, frankly, staggering.
Yeah.
What we're looking at is a 14 billion parameter video generation model running at 19.5 frames per second.
On a single GPU.
Exactly, a single NVIDIA H100.
And it natively supports text-to-video, image-to-video, and video-to-video generation.
Right out of the box.
So for all the ML engineers and AI researchers tuning in, here's the real hook for you.
Right.
It achieves minute scale generation without typical anti-drifting heuristics. So like no self-forcing rollouts.
And it completely drops standard acceleration techniques. I mean, there is no KV cache here, no sparse attention, no quantization, no complex sharding frameworks.
None of it.
They pulled this off by compressing the sampling steps from 50 down to just 3.
Using adversarial hierarchical distillation.
Yeah, and by radically cutting attention FLOPs.
Okay, let's unpack this. Because our mission for this deep dive is to figure out how these researchers actually broke the compute bottleneck of AI video generation.
It is a huge bottleneck.
It is.
Uh-huh.
And to truly appreciate what Helios is doing, we have to look at the massive wall everyone else has been hitting with diffusion transformers, or DITs.
Right.
Right now, most mainstream models can really only generate about 5 to 10 seconds of coherent video.
On a good day.
Exactly. And if you try scaling up to a massive 14 billion parameter model, something like 12.114b, it takes roughly 50 minutes to generate just 5 seconds of video.
On an A100.
Yeah, on an A100. The compute cost isn't just high, it is completely prohibitive for any real-time application you might want to build.
It's a massive barrier. I mean, if you look at the current landscape of attempts to achieve this real-time generation, the trade-offs are incredibly painful for researchers.
Usually they just rely on heavily distilled models, right?
Yeah, shrinking them down to around the 1.3 billion parameter mark.
Yeah. Which is great for speed, obviously, but terrible for quality.
Oh, absolutely terrible. When you shrink the capacity that much, the model just completely loses its ability to represent high-frequency details.
Yeah.
Complex motion turns into a blur, the textures wash out, and the whole thing ends up looking like it was shot through a jar of Vaseline.
Which nobody wants.
Yeah.
But then alternatively, if you refuse to compromise and you really want to keep that 14 billion parameter scale while getting interactive speeds, you were typically looking at requiring a massive 8-GPU cluster.
And as anyone who has actually tried to deploy across an 8-GPU cluster knows, that means dealing with complex tensor parallelism, dealing with node communication overhead, and essentially just setting a pile of money on fire to keep the servers running.
Just to get a short clip. And if you try to push past that 5 to 10 second barrier to generate long videos, like you would need for game engines or interactive environments, you run into the dreaded drifting problem. We all remember those early AI videos where someone starts eating spaghetti and then like 3 seconds later their face just melts into the bowl.
Yeah, that is drifting in a nutshell. It is essentially when the video forgets its original context and slowly falls apart the longer it runs.
Right.
The spatial layout breaks down, the visual identity shifts, it just stops making sense. Now, the common way the community has been trying to fix this is by using train as infer self-forcing rollouts.
I have always found that approach so brute force. Just for our listeners who might not be working on the training side of things, what does that actually look like in practice?
Basically, it means explicitly unrolling the diffusion process over long sequences during the training phase itself.
Okay.
You are forcing the model to generate and process long contexts so it learns how to handle them, but the overhead on that is brutal.
I can imagine.
It is slow, it is incredibly memory intensive, and it severely limits how far you can actually scale your model before you simply run out of VRAM.
Which brings us to Helios. Because they bypass those heavy, inefficient rollouts entirely. Instead of fighting the architecture with massive compute, they structurally changed how the model handles infinite generation.
And what's fascinating here is a mechanism they introduced called unified history injection.
Okay.
They essentially took a bidirectional pre-trained model, which normally looks at the whole sequence at once, and they converted it into an autoregressive generator.
Wait, let me stop you there. Usually, if you want a bidirectional model to generate sequentially, you have to slap causal masking onto it, right?
Yeah, normally, yes.
You mask out the future token so it can only look at the past.
That is the standard way. But causal masking fundamentally shifts the model's inference regime. It disrupts the pre-trained weights, which usually forces you into heavy step distillation just to get the model functioning properly again.
Oh, I see.
So Helios avoids causal masking entirely using something they call representation control.
Representation control. So how does it know what task it's supposed to do if it's not using mass to control the flow of information?
It is remarkably elegant, actually. They set up the input to the model as a simple concatenation of two distinct tensors along the sequence dimension.
Okay, two tests.
First, you have the historical context, which we will call xhist.
Right.
Second, you have the noisy context that is currently being generated, which we will call xnoisy. The brilliance here is that by simply altering what is inside xhist, the model switches tasks automatically without changing the architecture at all.
Oh, that makes total sense. So if you pass an xhist tensor filled entirely with zeros, the model looks at it, realizes it has no visual history, and instantly knows it is supposed to be doing text-to-video generation from scratch.
Precisely. And if only the last frame of that history tensor is non-zero, it treats that single frame as a starting image, and it switches natively to image to video.
That is so clean.
And if the history tensor is filled with previously generated frames, it seamlessly performs video-to-video continuation. It unifies all three tasks. But the real magic happens in how the model processes these two contexts using what they term guidance attention.
Right, because if you just concatenate them, wouldn't the noisy context corrupt the clean historical context during the self-attention process?
That is exactly the danger. xhist contains clean, already generated content. It shouldn't be denoised, and it definitely shouldn't be altered by xnoisy.
Right.
So they lock the time step of xhist at 0 throughout the entire denoising process. It acts as a pure, stable anchor.
Okay, locking the time step makes sense conceptually, but mechanically, how does the model actually enforce that separation inside the attention layers?
When the self-attention layer computes the query, key, and value tensors for both contexts, they introduce learned amplification tokens specifically to modulate the historical key.
Amplification tokens?
Yeah, what this does is selectively amplify or attenuate the historical information on a per-attention head basis. It forces the model to focus only on the most discriminative and useful parts of the history, completely suppressing any redundant or harmful noise.
I see. So it's dynamically deciding which parts of the past are actually relevant to the current frame being generated. And I noticed in the paper they made a really specific optimization regarding the semantic text prompts, too.
Yes, they did. Through cross-attention, the text prompts are only injected into the noisy context, xnoisy. They are completely kept out of the historical context.
Because injecting them into the history would just be redundant computation. Like the history was already generated based on that prompt.
It definitely saves compute, but more importantly, it prevents semantic accumulation.
Semantic accumulation.
Think about it this way. If the text prompt says a fluffy cat, and you keep injecting that prompt into the historical frames over and over again, the attention mechanism might start compounding that feature.
Oh, right.
By frame 500, you don't just have a fluffy cat, you have an impossibly giant cloud of fur taking over the entire screen. Restricting the prompt to just the noisy context stops that runaway accumulation.
That is such a smart, clean way to handle it.
Yeah.
Which really leads us to how they actually manage these minute scale videos without everything falling apart. Because I really appreciate how the researchers didn't just accept drifting as some vague, inevitable problem.
No, they didn't.
They actively categorized the failure modes of long video generation into 3 distinct shifts.
And breaking these down is absolutely key to understanding how Helios generates infinite, coherent video without relying on those heavy self-forcing rollouts we talked about earlier.
So what are the 3 shifts?
The researchers categorized them as position shift, color shift, and restoration shift.
Let's start with the position shift. This is that bizarre phenomenon where you are generating a long video and suddenly the scene snaps back to an early position, creating this weird repetitive motion.
Right.
It's like a needle skipping on a record player. Why does the model suddenly decide to loop like that?
The root cause is absolute temporal indices. Existing long video methods typically use absolute rotary position embeddings, or ROPE, along the time dimension.
Let's pause and just translate that for anyone who might be a little fuzzy on ROPE.
Sure. Positional embeddings are basically how a transformer knows the order of a sequence.
Right.
If you train a model on 5-second clips, it learns to understand temporal positions from, say, frame 0 to frame 120. It builds a very specific mathematical understanding of what frame 100 looks like.
Okay.
But during inference, if you try to generate a 60-second video, the model is suddenly fed temporal index 1000 or 1400.
And it freaks out.
Exactly. It has never seen those numbers during training. The multi-head attention mechanism doesn't know what to do with that index, so it essentially panics. It defaults back to early positions it actually recognizes, which causes the video to snap back and repeat.
It's literally like asking someone for directions in a city they've never visited. They just point you back to the only landmark they actually know.
That's a great way to put it.
So how does Helios fix this?
By using relative ropey. Instead of letting the temporal index grow infinitely, Helios forces the temporal index range of the historical context, xhist, to always remain relative.
Relative to what?
Specifically from 0 to a fixed number, thist. The noisy context simply picks up immediately after that. Because the model is always looking at a sliding window of time, it never encounters an unseen temporal position, regardless of whether the video is 5 seconds or 5 minutes long.
Wow, it just completely eliminates position shift at the source.
Yeah.
That is brilliant. Now, what about color shift and restoration shift? Because this is where the video quality degrades, right?
Right.
The colors wash out, contrast disappears, or the structural integrity of the objects, it just melts away over time.
Yeah, and to combat this, instead of doing those expensive self-forcing rollouts, Helios explicitly simulates drifting during training. It is essentially like vaccinating the model against degradation.
Vaccinating the model.
Yeah.
How do you simulate drifting without actually rolling out the long video?
They use two main techniques for this. First is first frame anchor, which ensures that the visual identity is tightly locked to the very first frame of the sequence.
Okay, that makes sense.
Second, and more importantly, is frame-aware corrupt. During the training phase, they deliberately inject specific types of noise and degradation into the historical context. They artificially wash out the colors or blur the edges of the training data.
Ah, I get it. So by feeding the model slightly corrupted history during training, it learns not to over-rely on perfect pixel-level fidelity from previous frames.
Precisely.
It learns to extract the broader global context, even if the history is a little messy.
Exactly. It forces the model to be robust. It learns to correct those errors natively, providing all the stability of long rollout training without actually having to compute those massive, expensive long rollouts.
Here's where it gets really interesting. Let's talk about the token-level math.
Yeah.
Because everything we have discussed so far explains how it generates long video, but we need to talk about how it generates video fast.
Right, the speed.
How on earth do you get a 14 billion parameter model to run at 19.5 frames per second?
It is entirely about identifying and eliminating redundancy. When a model performs autoregressive prediction, it relies very heavily on the most recent frames to understand local rapid motion.
Sure.
If I throw a ball, the model needs the last few frames to calculate velocity and trajectory. But distant frames, frames from 10 or 20 seconds ago, are really only needed for coarse global context.
It's kind of like human memory. If I ask you about a conversation we had 5 minutes ago, you can remember the exact dialogue.
Yeah.
But if I ask you about a vacation you took a week ago, you compress that memory into just, we were at the beach. You don't need the high-frequency details.
That is a perfect analogy. You don't need pixel-perfect high-frequency detail from a minute ago just to remember that the background of the video is a forest.
Right.
So they created multi-term memory patchification to compress that distant history. They apply progressively larger patch sizes to older frames in the historical context. The further back in time a frame is, the more aggressively it gets compressed into fewer tokens.
Okay, so what kind of reduction are we talking about here?
This hierarchical approach reduces the total number of tokens in the historical context by approximately 8 times.
Wow. And for anyone who works with transformers, you know that attention complexity scales quadratically with the sequence length. That L-squared term is the absolute bottleneck in any architecture.
Exactly. The per-layer complexity for self-attention is dominated by the square of the sequence length. So if you reduce your token count by a factor of 8, your attention FLOPs don't just drop by 8.
They drop by 8 squared.
Yes. That is a massive 64 times reduction in attention FLOPs for the historical context, and it's done completely natively without any sparse attention hacks.
That is a staggering optimization. But they didn't stop at the history tensor, did they? They also compressed the noisy context, X-noisy, using something called the Pyramid Unified Predictor Corrector.
Right. They essentially reformulate the flow matching process. Instead of running a trajectory from full-resolution noise to full-resolution data, which is highly expensive, they run multiple trajectories from low-resolution noise to multi-resolution data.
Okay.
This reduces the tokens in the noisy context by about 2.29 times, which yields roughly a 5.2 times reduction in attention FLOPs for the generation side of the equation.
Okay, so they've slashed the token count across the board.
Yeah.
But even with all those tokens compressed, you still have the problem of sampling steps.
You do.
Standard diffusion models need around 50 sampling steps to generate a high-quality output. Doing 50 forward passes of a 14 billion parameter model is never going to reach 19.5 frames per second, regardless of how few tokens you have.
Which brings us to their third massive optimization, adversarial hierarchical distillation. They managed to distill the sampling process from 50 steps down to just 3 steps.
3 steps. Okay, let me play devil's advocate here. Standard distillation, like distribution matching distillation or DMD, usually relies on a multi-step teacher model.
Right.
The student model tries to match the teacher, but in doing so, it usually inherits all of the teacher's biases. It ends up predicting an average of the probabilities, which is why distilled models usually look kind of blurry. How do they do 3 steps without it looking like a smeared mess?
You are entirely right about the average problem in standard distillation. Helios avoids this by taking a purely teacher-forced approach using the autoregressive model itself as the teacher.
Okay.
But the real key to maintaining sharpness is that they augment the distillation with an additional non-saturated GAN objective.
A GAN objective, as in generative adversarial networks.
Yes. They introduce multi-granularity classification branches distributed across the DIT layers. Essentially, they add a discriminator that looks at real ground truth data to provide supervision that is entirely independent of the teacher model.
Oh, wow. So instead of just trying to copy the teacher's smoothed out homework, the GAN discriminator is actively punishing the model if the image doesn't look razor sharp and realistic.
Exactly. This GAN objective pushes the model to generate highly realistic, sharp details that standard distillation would normally blur out. And crucially, by integrating this adversarial training, they completely eliminate the need for classifier-free guidance, or CFG.
That is a massive point that might fly under the radar for some. In standard inference, CFG requires you to do 2 forward passes per step, 1 condition on the text prompt and 1 unconditional, and then you mathematically extrapolate between them to force text alignment.
Right.
By eliminating CFG, they instantly halve the number of forward passes required during inference.
And if we connect this to the bigger picture, all of these token reductions and step compressions don't just result in blistering inference speeds, they radically transform the infrastructure requirements for training.
How so?
Because they slashed the token count and the resulting memory overhead so aggressively, the researchers were able to fit up to 14 billion parameter models within a single 80 gigabyte GPU during training.
I just need to repeat this so the ML engineers listening fully grasp it. 4 13B models inside a single 80 GBB GPU. That completely shatters the normal paradigm.
It really is.
Usually you are fighting with Megatron LM or DeepSpeed, dealing with complex tensor parallelism or pipeline sharding, just to train one model of that size without throwing a CUDA at a memory error.
It drastically simplifies the engineering stack. They can train with batch sizes comparable to standard image diffusion models, operating entirely on 64 standard NVIDIA H100s without writing any complex parallelism code.
And they wanted to prove that this wasn't just theoretical speed, right? That the quality actually holds up over time. But there was a problem. There was no standard open source benchmark for real-time long video generation. So they built one themselves called Helios Bench.
It is a vital contribution to the community. Helios Bench comprises 240 distinct prompts spanning 4 different duration regimes.
Okay.
They test very short videos at 81 frames, short at 240 frames, medium at 720 frames, and long videos at 1440 frames.
And looking at the charts in the paper, Helios consistently outperforms the competition. Whether you are comparing it to small 1.3 billion parameter models or other massive 14 billion parameter-based models, Helios wins on visual quality, motion dynamics, text alignment, and robustness against drifting.
All while leaving them completely in the dust on throughput.
Absolutely.
It really is a testament to rethinking the architecture from the ground up, rather than just throwing more hardware at the problem. By solving token redundancy and rethinking temporal indexing, they unlock speeds that were previously thought mathematically impossible at this parameter scale.
So what does this all mean? For you listening, whether you are pulling your hair out, prepping for a model deployment, researching new architectures, or just trying to keep your AWS budget under control, Helios proves a critical point.
Definitely.
Massive parameter scale does not strictly require massive inference latency. If you fundamentally rethink how your model handles token patchification and history compression, you can have a 14 billion parameter behemoth flying at interactive speeds on standard single GPU hardware. It completely changes the calculus for deploying large video models.
It certainly does, and it leaves us with a really profound implication for the future of interactive media. The paper explicitly mentions the potential of diffusion models serving as world models for game engines.
Wow, okay.
Consider what it means for the future of interactive digital environments. If a 14 billion parameter video generator can run at 19.5 frames per second on a single GPU, we're approaching a very real threshold here.
We really are.
Could real-time inference via diffusion eventually replace traditional 3D rendering pipelines entirely? Imagine a future where we are rendering sprawling, interactive video game worlds not from polygons, textures, and ray trace shaders, but directly from compressed history tokens hallucinated on the fly by an autoregressive transformer.
It completely reframes what a game engine even is.
Exactly.
You just boot up a AAA game and there is no graphics engine, just a diffusion transformer generating the world in real time based purely on your inputs.
That is definitely a provocative thought to mull over.